Right. So assuming we have enough people to start. We have enough people to have a look all together. So give me a second. Let me just sort out a few more things, and there you go. And if you have any questions, please feel free to raise your hand or type your questions. So I'm more than happy to have a look at any questions during the session. But you're gonna have some time to ask a few extra questions later on. Right. I'm sure you have your values from the lab or your experiment with you. So I'm sure you will have no trouble to compare, say, my values, which are all, say, I made. Anyway, so let me have a look at the first one. So I'm going to upload this slide after today's session on the week 2 module content. So I'm going to have I'm going to name differently because there's another identical file. Anyway, so this is what we did, and to say find out what the reaction can do in terms of say energy, right? So I'm not sure whether I mentioned this on in the lecture last Friday, but the content covered in the first lab needs to be will be covered in week 4, and because of that, some people might wondering whether you guys need to do a lot of research. And if you want to be 100% precise, I don't mind you spending extra time. But as far as I understood, and you don't really have to spend a lot of time to find relevant information. It was just say little bit of there was a little bit of say miscommunications going on. So that is why we started doing this lab rather than next lab. So apologies, guys. All right. So when it comes to thermodynamics, although you spend some time to measure, say, temperature changes, but later you will see it really is not really useful information. Although you could see some changes, and you could see later on that is the reason why you had some errors, right? And I will leave the readings to you, but the dot points over here will be a fairly important concept to go through the content in week 4, right? Okay, and most importantly, somebody might, not all of you, but some of you might have some, say, misunderstanding, because by doing the calculation, you expect to have negative values, but it is not true. So the value you are using are all positive. So because of that, you wouldn't be able to get any negative values unless you made a catastrophic mistake during your experiment. The thing you need to do is, once you finish calculating your values, either delta H or Q should be positive anyway. So once you get your final value, say to express the changes of the energy in the system, you just need to simply put negative sign. So that is all you need to do, right? So part A is calculating or finding out the heat capacity of your calorimeter. And it is somewhat not necessary, but because it is better to do to have a accurate result. So that is why we measure the heat capacity of calorimeter. The reason why we did was because measuring, say, energy directly is really, really hot. So because of that, what we do is we say take the initial temperature and then final temperature. Then we find out the differences later on. We can always calculate into changes in energy. So that is what we did. But the issue with the calorimeter is because the calorimeter is also made with something. So either it's going to be plastic or metal, depending on what you are using. So regardless, so all the say metals or materials, they tend to absorb energy. So let's start drawing something. Although my drawing is not great, but I'm sure it'll be better than me keep talking. So by putting a thermometer, you can measure, say, changes of the temperature, because most of the heat from a reaction or putting hot water into this system, you should be able to see some changes in the temperature, but say a certain amount of, say, energy will go on to the surface of a calorimeter. So because of that, we can capture the all the energy transfer. So that is why we measure the heat capacity of the calorimeter. And by doing this, we can also put the energy not measured using the thermometer. So we can put those amounts of energies into the calculation. So the result will be, say, more accurate. Okay, so the equation you have in your lab book is like that. And so instead of using this equation, because in terms of, say, expression, I would say it is not 100% correct in terms of, say, thermodynamics. I mean, I have no trouble using, say, T1 or T2. But say in terms of communication, if you don't really memorize what T1 is for and T2 is for, it might be a bit confusing. So because of that, I would use TC for the temperature from the cold water, and then TH for the temperature from hot water. And then this one, TM, let's call it T mixture. So I was okay with TM. But instead of calling T1 for cold water and T2 for hot water, I would call TC and then TH. And when you look at the temperature changes over the time, you will see temperature going down when you did your first experiment, because there's nothing going on within the system. So because of that, you'll see temperature going down. And when we do measure, say, changes in energy using calorimeter, we really want to do in a 100% isolation from surroundings. So this is a thing called the system, and then out of the system will be surrounding, and the surrounding could be, say, air, or could be, say, anything. And then when you combine both surrounding and the system, we just simply call it universe. And when it comes to doing, say, calorimeter experiment, and calorimeter should be able to provide 100% isolation, but I'm sure. Okay, let me find something straight so I can draw at least a straight line. So, assuming you measured only 1 minute, I know you measured for 3 minutes, and I am doing something similar, but it's not going to be identical. But I'm sure you have no trouble understanding or translating this graph into your graph. So it should be temperature, and then it should be time. So initially you had a certain, say, temperature. It all depends on, say, the temperature of hot water. So and then once you mix and then put it into a calorimeter over here, say, your temperature started at 40 degrees Celsius, and it'll slowly go down. So it could be really hard to see the changes, but I am exaggerating the changes. So after a certain time, it reaches 30 degrees Celsius. Right. So ideally, again, calorimeter should be able to provide 100% isolation, but because of the limitation, this is what we had. So obviously, temperature should be decreasing, but if it can provide, say, 100% isolation, your temperature should remain at 40 degrees, regardless of time you spend. So say this is like 1 hour, 1 hour. So this will be time, and this will be our temperature, right? So that is the complication we had, and this should be the largest factor affecting the accuracy of your result. Okay, so when it comes to using the temperature, so that is what I'm gonna do. So have you guys seen time as a say one of the variables in the equation? No, right? So regardless of how long it'll take, so thermodynamics or anything related to thermodynamics is mostly based on initial and final, right? So you need to make a decision. So which one should be the final? So since we are talking about changes of the initial and final, so when it comes to say heat producing reaction or exothermic reaction, you always want to look for temperature initial. So let's call it initial temperature, and then final or maximum temperature. That these two are the ones you need to look at. And this one over here, because it really doesn't specify which one you want to use. So my recommendation will be initial temperature of your, say, hot and cold water, as well as temperature you measured at, say, highest. So if your graph is, say, graph is instead of going down, if you see your temperature going up and down, I still would use temperature you measured, the highest temperature you measured. Because if you, say, take a temperature somewhere around here, you already lost a lot of energy through the calorimeter. So temperature you're going to use, if you decided to choose temperature over here, it is not going to be as accurate as the one you saw at maximum. Right? Okay, so when it comes to the calculating heat, so it can be a capital Q or small q. So this will be one over here, right? So this will be QH, the one in the square bracket. And then the other one in the other square bracket will be heat, say, transfer from cold or mixed water to cold water. So we're gonna calculate these separately, and then use these values into the this equation. So I made a series of numbers. So what I'm gonna do is I'm gonna use these values, and I'm sure you will have no trouble using your values. So in the end, so delta T in my case, it will be 17 Kelvin times by since it was 50 milliliters. So using the density of water, which will be 1 ml equals 1 gram. So it can be simply translated into 50 grams. right? So 50 gram over here is from the volume you used, then times by heat capacity of water, which is 4.184 joules or Kelvin per gram, right? So once you do, you should have so Kelvin cancels out, gram cancels out, leaving numbers in joule, right? So you should have some numbers over here, and then you do the same. So it'll be say 15 K times by 50 grams times by heat capacity of water 4.184 joules per Kelvin per gram. So you also should have a certain value in joules, right? So once it is done, you use these values into the final equation, which can be simplified like this. So the equation you have in your lab book is a extended version of the equation you are seeing over here. You just need to simply upload those numbers into this equation. So when you do it, let's just do a quick calculation because I just don't want to skip this process. So 17 times 50 times 4.184. So I have around 3,500 and 3,500 joules, and QC I have is 15 times 50 times 4.184. So I have around 32 joules, 3,200 joules. So since it is already calculated, we're going to plug these numbers into this equation. So QH is at 3,500 minus around 3,200. That should be in joules, and then divide by temperature changes from mixed to cold, which is at 15 K, right? And once I put these numbers into my calculator, divided by 15. Mm-hmm. So I have around 28 joules per Kelvin, right? So heat capacity from my values. So again, these are all these values are the ones I made to say give an example. So please use your value. So based on the numbers and based on the results I have, and the heat capacity of the calorimeter is at say 28 joules per Kelvin. So which means if the system experience 1 degree changes in Kelvin, it'll this much energy, 28 joules of say energy will go into the calorimeter. So that is what we have. But normally the plastic, because the calorimeter we are using were made with the plastic. So ideally, the heat capacity of plastic will be this small. But because we will just keep losing the energy through the wall of the calorimeter, the number is more than 10 times higher than what it's supposed to be. So what I'm going to do is I'm going to write it down here, because when I change the page, I will lose these numbers, right? Okay, now next one is when we observe the temperature increasing, so exothermic reaction. Okay, now let's use blue color. Right. So it'll be pretty much the same process, except the calculation is a little bit different because you need to find out the enthalpy changes. Anyway, so based on what you guys did, so these are the ones, the reagents you are using. and the molarity, the concentration of each one was at, say, 1 molar. 1 molar HCl and the 1 molar sodium hydroxide solution. And as soon as you mix, because these two, so once you have these ones, these are the ones you have in your solution. But as soon as you mix them together, acid or proton and then OH minus, they will start reacting, forming so from here, because it is a reaction within an aqueous environment or a reaction in solution. So what I'm going to do is I'm going to write the ionic equation. So H plus Cl minus plus Na or H. No, hang on. Sorry, Na plus OH minus forming Na plus Cl minus plus H2O. Right? By mixing, say, hydrochloric acid and sodium hydroxide solution, you simply made salt water. And if I'm sure all of you still remember what you did in your first chemistry course, if you did chemistry 1, and if you haven't done chemistry 1, I'm sure it is fairly simple to understand. So by looking at the changes, when you look at sodium and chlorine, there's no changes at all, so we can cancel them because they're not really participated in the reaction, so they're going to be spectators, leaving H plus OH minus, making water. Right. So this is the net ionic equation. So by having these two, you can make water. And I'm sure you are also temperature going up compared to the initial temperature of each one. Right. So because of that, you can already tell it is going to be an exothermic reaction. And although, depending on how you did and how you mix, so some of you might have, so that let's call this one is temperature, and then let's call this one is x is time. So some of you might start at, say, higher temperature, and then the temperature going down slowly, or if you start measuring temperature before you turn the sort of plate, temperature will slightly go up, and then it will go down. So if you see temperature going up a little bit and going down, again, the time really doesn't matter because you need to find out the temperature max and temperature initial. So the highest temperature you observed will be the temperature you want to use. And if your, say, graph was going from, say, highest to lower, so this temperature will be your temperature final or temperature max, depending on how you did. So I made some numbers to show you what was happening. So I'm sure you measured your acid and base temperature separately. And if you're not too sure which temperature you want to go for, the best way will be, so your initial temperature will be average, right? So if your, say, T acid is at, say, 23 and base is 24, you can average them together. T base divided by 2 will be T initial. And then our final temperature has to be the maximum temperature you observe. Maximum temperature you observed during your experiment. And if you have, say, 23 degree for acid and 23 degree for base, you can simply choose 23. But if you see temperature difference, please make sure you average your temperature to find out the initial temperature, right? And then assuming my final temperature was at 30 degree, you can simply calculate delta T, and my delta T is at 6.5 K, right? So now to find out the heat released from the reaction, you use the same equation. So in my case, so delta T is 6.5 K times 5 mass. Mass needs to be total mass, because without mixing, say, 50 grams of acid, do we have any 50 grams of acid, 50 grams of base. So without mixing, say, these together, you won't be able to see any heat from the reaction. But when this system start, say, producing heat, the energy goes into the entire system. So because of that, mass needs to be total mass. And then when it comes to heat capacity, so there might be a little tiny bit of difference, because now instead of having only water, you have these ions. So heat capacity might be a little bit different, but difference is too small to be noticed for your in your calculation. So because of that, you can simply use heat capacity of water, because your solution is mostly made with water. So what I'm going to do is I'm going to use heat capacity of water, which is 4.184 joules per Kelvin per gram. Right? So once you put these numbers into your calculator, 100 times 5, 4.184. So I had 2700-ish. So that is the energy from the reaction, right? So this is the energy produced, measured using your thermometer. And as I mentioned beginning, so some of the heat will directly go to the calorimeter. So we need to put the heat loss from the calorimeter. So this is the way we calculate the heat. And based on the previous calculation and the temperature changes in part B, so 6.5 K is the temperature change. And the heat capacity of the calorimeter I had using the values I made up. So I have 28 joules per Kelvin. Because temperature change was 6.5 Kelvin. And by simply multiplying these two, you should be able to get the numbers in joule. So 6.5 times 28. And so 6.5 times 28. So I have 182 joules. So that is the energy transport, heat transport directly to the calorimeter we are using. And lastly, to find out the enthalpy, and because you need to find out the enthalpy, you need to use the energy from the reaction, which is Q reaction plus Q calorimeter. Hang on. Right. So it doesn't say how we find out the Q total, but I'm sure you guys are smart enough to figure it out. Plus Q calorimeter, right? And then divide by number of moles of your reagent. So since we had 50 mils of 1 molar acid and base, so number of moles of HCl will be 1 moles per liter times 5 50 mils, so it should be 0.05 liter. So in the end, you should have 0.05 moles of acid as well as same number of moles of base. Right. So although we added mass together, when it comes to the number of moles, you will need to say use number of moles of HCl or number of moles of NaOH. So if you don't have equal numbers of moles, so assuming you had say 0.06 moles of HCl and then 0.05 moles of sodium hydroxide, if that's the case, you want to go for the number of moles of your limiting reagent. So to be a limiting reagent, you should have a smaller number than the other reagent. The reason why you want to go for the smaller number of moles of one of the reagent will be this limits the reaction, and if there's no more reaction, there'll be no more energy coming out, right? So if that's the case, you want to go for the limiting number of moles of your limiting reagent. But since we have the same number of moles, so it is not going to be an issue. So heat from this reaction will be 2720 plus 182. Then divide by. So I have a big number, which is normal. So total number of heat is 2902 joules, and the number of mole is 0.05 mole. Right. But once you finish calculating, you expect to have 58,000 joules per mole. Right. So since it's a big number, we can just simply say 58 kilojoules per mole. So that is the say changes in enthalpy from the reaction. And as I mentioned in the beginning, since it is an exothermic reaction, instead of leaving this number as a positive number, just put the equal sign. You will need to put a negative sign to express this was an exothermic reaction. So the reason why we put a negative sign is because although we saw temperature increasing and then our energy gaining from the reaction, when you look at the system itself, it lost this much energy by mixing, say, acid and base together. So because of that, we need to put positive sign. So if it's endothermic, on the other hand, you need to put a positive sign, right? And this is just extra information. You can have a look. So assuming you exactly have same amount of different types of acid and base, when you finish in reaction, the energy or both energy and then changes in enthalpy should be similar because this one will be spectators, right? So in the end, your net ionic equation will be H plus OH minus making water, right? So assuming all the setups are identical, and then molarity and the amount used are identical, you should have a very similar value when you did use different types of acids or bases. Right. And okay, so when you look at the next part of the last part of the experiment, the only difference between part B and part C will be the acid, right? And molarities are the same, the amounts used are the same. But when you look at the acid itself, it is not as strong as previous acid you are using. because now we are looking at acetic acid, which is a typical example of weak acid. And when it comes to weak acid, they don't really fully say dissociate, or they are not exist as a ion all the time. Because of that, so when you look at say acid only, so you will see a dynamic equilibrium existing. Right. So as soon as you put this one into water, it will produce proton, which is an acid, and then acetate ion. And because this is a weak acid, some of the say protons in the system will try to go back to acetic acid. So we can see dynamic equilibrium going on. So once you have a weak acid in the system, so some of the energy produced from say acid-base reaction will be used to put this one into this one. So in the end, the temperature changes you see will be a little bit smaller than the one you observed from part B. In terms of say acid strength or pK value, if you remember the meaning of pK value. Anyway, so regardless, if you don't see differences, that is all good, but that is what you expect to see. And sometimes things don't go well. So because of that, you might have a higher temperature difference than part B, which is also fine. As long as you understand what we are looking at, I'm more than happy. So it's the same process. So some of you might have temperature and then time, right? So temperature going up and down. So in some cases, you might have say temperature going from as highest temperature to your say temperature in say 3 minutes. It doesn't matter how the graph it look like, as long as you find out the maximum temperature you observe. So if your maximum temperature is studied in the beginning, use this temperature. And if your temperature was going up and down, use temperature at maximum. That is what you need to do. And same again. So I have numbers over here. And so initial temperature should be 23.5 degrees Celsius. And final temperature, again, I made up this number because it needs to be smaller than the one from hydrochloric acid. But if I do, I might have higher temperature or same temperature because I didn't do the entire experiment while I was running a lab class from 6 p.m. to 9 p.m. Anyway, so it'll be the same process. You use delta T, and the mass will be total mass. Right? And then heat capacity, same as previous one, use heat capacity water. So the heat from the reaction will be 5.5 Kelvin times by 100 grams of acid and base mixture times by 4.184 joules, not grams, joules per gram per Kelvin. And then in the end, just check. Right? You should have a number in joules. So what I have on my calculator is 2300 joules. So that is what I have. And the heat, we couldn't, the energy or heat, we could not measure using the thermometer, which directly goes into the, went to the calorimeter. The same process. You can use heat capacity of a calorimeter, and then temperature changes. And so I was 28 joules per Kelvin, right? So 5.5 times by 28. So I have 154 joules. And then when it comes to the enthalpy from the reaction, it'll be pretty much the same process. So will be 2301 plus 154 joules divided by. So the enthalpy I should have will be about 49 kilojoules per mole. And then again, this was an exothermic reaction. So compared to the initial and then our final temperature went up. So because of that, you need to put negative sign. I think that is the all the calculations you need to do. And okay. And there were some questions asking about the largest source of error in this experiment. And when it comes to an error, I know a lot of people just simply say human error. And regardless of types of error, it could be random or systemic error, it is all from the human error. So if you simply write down saying it was because of human error, it doesn't look really, really good because you are just actively telling that you made a lot of mistake. So please do not use human error. Right. So as I mentioned in the beginning, temperature was going down, right? Regardless of how it looks. And when you, I am saying this one more than twice or 3 times. So when it comes to measuring, say, changes in enthalpy or measuring energy, it needs to be isolated from the system. But if you see temperature going down, your system was not actually providing good isolation. So that should be the largest source of error. So ideally, using strong acid, and if you manage to make water, so the number you expect to have should be around, say, 58 kilojoules or more. And then if it's weak acid, it will be, so in case of, say, strong acid, do it again. If it's a strong acid, it will be delta H should be around 58 kilojoules per mole. But if it's weak acid, it will be around 50 kilojoules per mole. So your value can be larger than the value over here. It all depends on also depends on the calibration. If you made a few mistakes, you're gonna lose a lot of energy through the calorimeter. And once you put those ones into the account, your value might be higher than this value. So this is a theoretical value, and you really cannot have larger than theoretical value. So if that's the case, say, assuming you say delta H it ends up like 70 kilojoules or more, and it is obviously incorrect, right? If that's the case, instead of using Q total over N, I would suggest you to have a look at number from Q reaction. Over N. By comparing, say, these values, so if you your calibration is incorrect, and once you find out another value using this equation, and that might be just minus 55 kilojoules or more, right? Then you can also tell your say calibration or your heat capacity measurement, or your measurement of heat capacity from your calorimeter is not correct. So that also can be the reason why you have a larger number than, or say, the value you expect to have, right? So, but in general, the largest source will be using calorimeter or having not enough isolation, right? And next one, how should the two heat subreaction? Okay, so this will be because of the types of acid. So the first one, part B, was using strong acid. So because of that, they are already fully say dissociated. So it doesn't need any extra energy for say dissociation of say acid from countering anion. So because of that, you expect to have a higher say energy from the reaction. And on the other end, if it is weak acid, some of the energy will be used for making acid from the acid molecule. So because of that, the enthalpy or the energy from the reaction will be low. So I simply said ionization, but it is up to you how you describe. So you don't really have to write a full say essay, as long as it explains why part C produces less energy. So it'll be much more. It'll be more than fine. And the last one, why wash and dry the thermometer between measuring HCl and NaOH temperatures? I'm sure you already know the answer. Without washing and drying properly, you are actively contaminating your reagent. Because of that, the energy from the reaction in the calorimeter or in the system will be smaller than what you expect to have, right? Okay, so let's quickly have a look at the template. So because I believe you've been told to use template, right? So based on what I see, you need to put your name and number. If you know your lab partner's name, put your partner's name. If not, I'm not sure what to do. I'm sure it'll be fine without a partner's name, and make sure you put your day and due is it correct? It's due 3rd of August. Okay, Kevin, you have a question?
Yeah, no, that's what he's got on the portal, Tack, which sort of put me on a bit of a back foot. And this is what I emailed Todd about last night. I said, we haven't even been presented with this content. It's not even released yet. Now I've got to learn all this and apply all this and submit before Monday.
Yeah. So has Todd, have you got a response or reply from Todd?
Not really as yet. I also emailed them again regarding the template because I'm not real good with Excel, and part of the problem is
if you're not good at Excel, just use pen and paper, or use print this one out and then draw X and Y.
Oh yeah, that'd be easier. He hasn't got back to me.
Yeah, I mean, it is up to you. So in the end, regardless of any software or any say way of doing presenting your result, in the end, it is because of the communication. So the reason why chemists use a lot of symbols and say drawings, because without those ones, we're gonna make a lot of mistake through the communication process. So that is the reason why we use say abbreviated say symbols and etc. etc. So in the end, it is all about communication. So as long as you can effectively communicate, as long as you can say communicate effectively, it'll be fine. So yeah, if you are competent using say ruler and pen, and go for it. Even you can use graph paper. So it is totally up to you. And okay, so question number 1 says, briefly describe the, hang on a sec, there are some questions, right? Yeah, so what I suggest you to do is delete this graph, delete the graph in the template, and then put your graph. Right, so if you use Excel, you can simply copy your graph from Excel and then paste onto the template. So that is what I would do. And you don't really have to label these ones. As long as you can present your graph, it'll be more than fine. So when it comes to, say, making graph, it needs to be based on your numbers, right? So you have to use your own number. Yep, you have to use your own data. Please do not use the numbers I used, because then we can tell you just copied and pasted onto your lab report. So that is why you will have to use your numbers. And again, so we really don't expect to have really good data, because I presume this is the first time you did the experiment, and we don't really expect you to produce a good set of data. So feel free to use your data, and as long as you use your data, regardless of how good or how bad they look, it'll be more than fine, right? Okay, so write 5 to 8 lines. This one. Briefly describe the principles of measurement of the heat of neutralization. Yeah, I don't understand why it needs to write 5 between 5 and 8 lines. As long as you write something, it'll be fine. So background principles. I mean, principle is already in the equation. I'm not exactly sure what kind of, say, measurement we are talking about. It could be, say, a measurement of heat or measurement of delta H. So if it's delta H, we are measuring, say, the standard heat of standard energy or standard enthalpy changes of the reaction. Or if it's heat, it is just energy changes in the system. And when I had a look at the lab books, the information we have in the lab is not even comprehensive. So I really don't know what we expect. So assuming I am marking your lab report, as long as you have something like this experiment is designed to measure the heat changes in the system during a reaction, or not during a reaction, after the, let's call it during a reaction. So this experiment is designed to measure temperature change during a reaction, during reactions, because we did two different types of reaction, and the delta T, temperature changes, delta T, and can be used to calculate the changes in energy. Or to demonstrate, oh, hang on. Yeah, I think that should be good enough. And that should be good enough. And if you want to talk about, say, measuring the heat capacity of the calorimeter, you can include and as a calibration, because the temperature changes you measure through your thermometer doesn't capture all the, say, energy produced from the reaction, etc., right? Yeah, I think it means 5 to 6 lines. So including the calculation. So as long as you have something, it'll be more than fine. And heat capacity of calorimeter. Now I'm sure you should be able to do it. So, but make sure you delete the example graph and put your graph, and then and you don't have any equation like say delta equals Q over N, right? Do you have any equation like that in your lab book? If you don't have any specific, say, equation, this is the one you want to use for your enthalpy calculation. And again, make sure you put a negative sign in the end once you get the numbers, because it'll be exothermic reaction. And I think I explained everything. Yeah. Okay, so is there anybody who has any specific questions? And if you want to check your calculation, you can always contact me. I'm more than happy to have a look at your calculation. But I'm sure you guys are all smart enough to figure it out. All right, so if you don't have any questions, I can stop recording.